So for those who are on Webex, you have to do two things to join this session. This is a joint problem solving, guided problem solving sort of session where we'll go through problems which are similar to your graded assignments, so that it's good practice for graded assignment. You have to join the Webex to listen to the audio and see the screen share that I have. And if you have any doubts, you can use the Webex chat. But for any of the questions I post, do not answer them on the Webex chat. You have to go to joinpd.com and put the code ijrzdc. So that's the code on the top right of your Webex screen. And once you put that code, you'll start seeing these slides. You'll see a version of these slides. And every time there's a question, there'll be a answer box that will pop up. You can answer the question on that. There's no submit or anything. Just put your answer there and you will see. Okay. That's the method. There's about I think 1 minute left, so we should sort of get started. So, okay, so let's wait for a couple of more minutes. So the question about graded working professionals and adjustments in the quiz, we have done that. About the quiz, we have changed the deadlines. We've relaxed them a little bit. So 7:30. So we'll get started. So once again, to repeat the instructions, those of you who are only on Webex, also go to joinpd.com and enter the code that you see on the top right, ijrzdc, and you can answer questions there. How do you answer questions? So anytime I put up a question, you will get a screenshot which looks sort of like this. You will get a box with where you can answer, or you will get an answer question tab on the mobile at the bottom right. You have to click on that and then answer the question. So this is how you answer questions. I think we've had quite a few sessions now, so I think people will be familiar with it. So I'm going to go ahead and start this session and give you the problems, and it's C, IJRZDC. Okay, the last letter is C. C for cipher, cat, like that. Okay, so this is how we start, and we begin right away with the first question, which has been put up there for you. It's a very illustrative question which brings out the idea of random variables and what they are and how to deal with them and how to do computations with them, etc. So we'll take a little bit of time with this particular question. So go ahead and look at that. I'll let you read it for a second, and then I'll tell you what I think is a good interpretation. So basically, Rajat has 15 marbles, 6 are green, 3 are red, and 6 are yellow. So the experiment that he does in this setting is he picks 2 marbles randomly from his pocket. Okay, so this word randomly sort of suggests a uniform distribution, and the way he picks the marbles are like that. So any pair of marbles from this set of 15 are likely to come out uniformly in this experiment. And there is a random variable that's defined in this setup, and that is basically, so he's drawn 2 marbles. You find out how many red marbles are there among those 2, and that number is your random variable x. Okay, so once again, so the experiment is very simple. We've seen some experiments like this before. So you pick 2 marbles at random from the pocket. The colors of those marbles are given for you, and the random variable x now is defined as the number of red marbles that have been drawn. Okay, so the question now asks for the probability that this random variable x takes the value 2. Okay, so that's the question. Probability of x equals 2. You have to enter a number, and I believe you can only enter a alphanumeric number on your on the on joinpd.com. Go ahead and do that. So remember, the answer is a probability. Okay, so if you're getting answers which are either less than 0 or greater than 1, then something is wrong. Okay, the answer is a probability. Probability that x equals 2. Once again, for those who are coming in late or you have never been to these kind of sessions, you answer the questions by going to joinpd.com and entering the code ijrzdc. You don't answer the questions on Webex. Okay. No, I'm not speaking at this point. I'm just giving time for people to work out this question. We are at the time when people have quiet time for people to think about and answer the question. Okay, there's already someone who's saying the course is so difficult. Okay, so I'll give one more minute, then I'll answer this question. Okay, so I think I see that quite a significant number of people in the audience have actually answered, and there's few people who have not answered. So it's time, I think, to see the responses. Let's take a look at the responses. So you have 0.02857. It's sort of It's like the answer, but you see these answers like 3 and 5. These are these cannot be right. I mean, this is a probability. Probability has to be between 0 and 1, and you can have 3 and 5 as the answer. There's 0.028, and there's also a 0.0142. It seems like half of that, but 0.028 seems like a very popular answer. There's also people who got slightly different answers. 0.111, 0.009, 0.2, 0.14. So it seems like it is. Okay, so let's go back and look at the question again, and then go towards the solution. So this is a very classic basic setting. So I'm going to use this setting in the solution to describe to you what a random variable is and how to go about computing probabilities for it. Okay, so this is so let's just talk about this. Okay, so this is quite important. Okay, so I actually had some. So please ignore the question on that box for now. Let me just go through and explain this. In fact, I had it set up so that it will come only in the next click. It's like an animation on Google Slides, but I think Join PD is just ignoring the animation. It's just showing everything. Okay, so let's just ignore that little box there and go through the situation. Okay, so far you can see in probability you have basically an experiment. This is so whatever is random, what happens is the experiment. The experiment has an outcome, and the outcomes are collected into a sample space, and the outcomes also have a distribution, right? So this is the main story. Okay. And let's look at the experiment and its setting. There are 6 green marbles, 3 red marbles, and 6 yellow marbles. Okay, so I like to write it down like this. It's sort of clear to you. The G1 to G6 are the 6 green marbles, R1 to R3 are the 3 red marbles, and Y1 to Y6 are the 6 yellow marbles. Okay. And you're going to draw 2 marbles at random. So what is the sample space? What are the outcomes? Okay. So the outcomes are the 2 marbles that you're going to get. You may get G1 and G2, right? You may get that, or you may get G1 and G3. You may get G1 and G4, so on. G1 and R1, G1 and R2, maybe all the way to G1 comma Y6. So you may get these guys. These could be your outcomes. Or you may get G2 and G3, G2 and G4, all the way till G2 comma Y6. So it's just a way of carefully going through pairs and counting them. Likewise, you can go G3, G4, G3, G5, like that, all the way to G3, Y6. So I've just put dot, 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 dot. And in this kind of a setting, a lot of things are implicit. So for instance, one of the things that's implicit is I'm going to say G1 comma G2 and G2 comma G1 are sort of the same in this setting. Okay, so this is how we sort of assume the randomness happens, because you assume you're putting in, you're just taking both the marbles, and you're not interested in saying which came first, which came second, and all. You're not so interested. You're just going to look at both of them together. Okay. So it doesn't matter whether G1 came first, G2 came second, or G2 came first. There's no first and second for you, right? So it's just the set is what matters. Okay. So if you look at it like that, the total number of outcomes in this sample space is this 15C2, this quantity, 2 things that you can take from 15, right? So there's various ways to count this out, and you'll get 15C2 in this count, and that is 105. Okay, so this is question about identical, non-identical. I'll let you to think about it. So this is how the identical is, I mean, you have to sort of separate them and think of them in this way to get the count right? So otherwise, this will simply not work. Okay, so this is what is the total number of outcomes in the sample space. Okay. So the distribution we take is that all these outcomes are uniform, and then it's equally likely. Okay, so every outcome out of this 105 is will have a probability 1 by 105. I can see there's lots of questions people are asking about when do you take combinations, when do you take permutations, this and that. But you can see this, you can see the way I've written it down. If I wrote down if the ordering matters, if G2, G1 matters and all that, then you get a different sort of situation. Okay. So this is just probability of one outcome in this distribution. So far I have not talked about the random variable x, right? So I haven't come to that yet. But before that also, I have a question for you, and that's there in this box. Is this situation, I mean, instead of taking both the marbles at the same time, it turns out you can also think of it as taking one marble after another, and then not worrying about which came first. Okay, so you shouldn't worry too much about that, and then you just think of the pair that you got in that fashion. And if you took one without replacement, if you took one and without replacement, if you took the other, and this scenario is actually very similar to the scenario I've put down here. Okay, so keep this in your mind. I don't know if people answered this question too much. You could have put down a question here uh, in response to what I've asked. I mean, some people are saying no, both situations are different, but think about it. If any calculation you do in the situation where the sample space is defined in this fashion, in the situation where you take so people are asking questions about why should you say G1, G2 is a different outcome from G1, G3, right? So see, there are 6 marbles, and I have to count. So for instance, if you pick one marble, right, there is 6 out of 15 chance of getting that marble to be green, right? If I don't distinguish between these 6 guys, and if I say all of them are the same, I'll count them only one, then I will get like 1 by 3 or something always, right? So you have to weight the marbles in some way according to how many are there, and this writing G1, G2 to G6 is a way of distinguishing how many of green are there and how many of red are there, how many of yellow are there. Only then you can do the probability calculations properly. Okay. If you don't do that, if you think all the green is just one, and if you only put a G in the sample space, you're not going to get many pairs of GG, right? So there are so many ways in which G and G can happen, right? So if you don't put G1 to G6 and account for it in this way, you'll only get one, and that doesn't help you. You understand? So if I keep saying G1, G2, G1, G3, all of them are the same, then I'm discounting this fact that there are so many greens and there's a very high chance of getting greens. It's like this, there's a high chance of getting yellow. The only way I can bring that in is to put in the G1 to G6, R1 to R3, Y1 to Y6. Okay, so this is how it works. Don't think about it for a while and sort of accept it. Okay, so when we say 6 marbles of green colors, 3 marbles of red color, 6 marbles of yellow, and we want to do probability calculations on random choice, you have to take G1 to G6, R1 to R3, Y1 to Y6. Only then you will get the correct weighting for how many greens you're likely to get and all that. Okay, so this counting is important. But I wanted to think about what's in the box. Okay, so this kind of sample space where you take 2 and you take 15C2, okay, combinations of 2 from a collection like this will give you the exact same answer if you think of it as you take one marble and then without replacement you take the next marble. Okay, you can do a calculation in that setting, and both these settings will give you exactly the same answers. Whatever calculations you have to do for probabilities, both of these will give you the same answer. Think about why that is true. One can prove it sort of rigorously, but that's not the point in this course at least. So it is true that these two are the same. So you can use these two settings sort of interchangeably. Okay. Now there is a closely related another setting which I will not discuss in this class, but at least if you, for instance, if you throw a die twice, right, then you will get something in the first throw, something in the second throw, and then that is not 6 choose 2 possibilities, that is 36 possibilities, right? So that's sort of different. Okay, so some sample spaces will look like this, some will look very different from this. So let's focus on this setting, and I'm going to try and tell you how to solve the problem in this setting. In this particular setting, you have to sort of do it like this. Okay, so you'll get the correct probabilities when you do in this fashion. All right. So anyway, I spent a lot of time on this. Let's proceed. We haven't come to the sample space. So let's go to that. Okay. So now the question is, what is a random variable? So far we've talked just about outcomes, and we've not talked about the random variable x. Okay, so I'm not sure how exactly a random variable was defined in the class. It is some function from the sample space to real numbers. So you take the outcome, and instead of looking at just the outcome, you associate some number with the outcome. Okay, for instance, in this case, the random variable x has been defined as the number of red balls that were drawn. Okay, so it is a function from outcomes to real numbers, right? So usually people write just x, okay, but x is a function from outcomes to the number. For instance, if the outcome was g1 comma g2, what will be the random variable x? It will be 0. Okay, why is that? Because g1 comma g2, there are two greens. Okay, there's no red, right? I want to count the number of red balls in g1 g2, that's 0. Okay, same way for g1 g3 g1 g6. Now when you have the outcome as g1 comma r1, the random variable will become 1. Okay, so the random variable is tied to the outcomes of the experiment very, very strongly. When you do an experiment, there is an outcome. The random variable is a function of that outcome. So usually you have to say something like how I've defined the random variable here. Okay, the experiment happened. There's an outcome. I'm not actually interested in the outcome. I'm only interested in a function of that outcome, which in this case is number of red balls drawn. Okay. So I put down here all the 105 possibilities. And of course, there's lots of dot, dot, dot to sort of illustrate how it will come. And you can see in how many cases I got 0. You can see, you can quickly go through and check. Hopefully, I've not made any mistakes here. There are, whenever a red shows up somewhere, I will put a 1. Okay. If two reds show up, what are the ways in which two reds can show up? It could be R1, R2, R1, R3, R2, R3. Right? So you have 3 possibilities where you have 2. Okay. So somebody is asking, when do you have these kind of things in real life? So you'll see later on. I mean, these are things. These are like basics. You know, don't worry so much about exactly where these basics will be used in real life. Real life has a lot of probability in it. When you use probability calculations, these things are all implicit. You'll keep doing it over and over again. Okay, don't ignore the basics, thinking that I only want real life. Okay, and you'll make so many mistakes. All right. So hopefully this is clear. Okay. So this part is the basic definition of a random variable. This is how a random variable is defined. You have to always go back to the outcome and then map the outcome to a number. Okay. So there's this question about why is there R1, R2? What about R2, R1? Why shouldn't you count that? So like I said, in my outcomes, I'm not going to distinguish between R1, R2 and R2, R1. Okay. So if I were doing that, I will get a different sample space. That's a different calculation. Okay. So we're not going to do it. We'll only take R1, R2 to be equal to same as equivalent as R2, R1, right? So that's the way we are counting. We're not going to distinguish that. Okay. So now from here, the answer is sort of clear, right? So how do you do this? If you want the probability that the random variable equals 2, okay, what is the meaning of the random variable being equal to 2? Okay, look at that. What's the meaning of the random variable being equal to 2? The outcome should either be R1, R2 or R1, R3 or R2, R3. Okay, so the outcome should be 2 red balls. Okay, so that's 3C2 or 3. Okay, so that's 3 outcomes that are favorable to you divided by the 105 total outcomes. So you get 1 by 35, and that will evaluate to 0.028, etc. Okay, so I think a lot of people are confused by why this sample space is chosen in this specific way. Why is it that you do G1, G2, G3, G4, G5, G6 as opposed to just G, 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 G? Okay, so now if there's no point in putting G, 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 G. As far as you should just say there are 6 green balls, right? And if I want to keep counting, and if I want to say, I want to give some weightage to the fact that there is 6. If I only put G comma G comma G, there's no, if once in a set, if you start writing G comma G comma G, there's no, they're not different, right? It's as if you have only one G. Okay. And if I don't distinguish between the G's and distinguish between the R's and distinguish between the Y's, I will not get the count of how many greens are there, the weightage given to green. So probability of getting green is higher, right? So I want that sense of that. So I have to structure my sample space in this way, okay? So think about that carefully, okay? So I think even in the previous session, we discussed this kind of sample space. So this is how it is done, okay? So let me not spend too much time on this, but this is the correct way of giving the correct getting correct proportion out. Okay, so you get 3 by 105. So notice this last point that I've put down here. So x equal to 2 is not the only thing you can calculate probability for, right? X could be equal to 0 and x could be equal to 1. Okay, notice what I've said there down below. In the previous class and all that, we talked about disjoint events, right? In this sample space, you can have subsets which are disjoint events. And when you have disjoint events that partition the sample space, disjoint events are very nice, right? And if you notice, x equal to 0 corresponds to one event, no red balls. X equal to 1 corresponds to exactly one red ball. And x equal to 2 corresponds to two red balls. These three events are disjoint in the sample space. So this is the disjoint, and they also partition. Together they include the entire sample space. Okay. So this is an important notion. So anytime you have a random variable and the random variable takes different values, the events defined by the random variable equal to 0, equal to 1, equal to 2, etc. All these guys are disjoint events. Okay, so remember that. This will help you a lot in doing calculations. Okay, so we've got the answer. I want to show you just two more things. Okay, one is just a quick method. Like I said, I wrote down the sample space, I wrote down the outcomes, I wrote down the random variable in great detail. But once you get used to these calculations, people usually do this very, very fast. Okay, so how do you do this in your head quite fast? You can do it in two ways. I've written both the ways here, and both of them, as you can see, give you the same answer. In this kind of scenario where you're drawing two balls at random and you want to think of them as uniformly distributed, probability that this random variable x equals 2 is same as the probability of both balls being red. And that's 3C2 by 15C2. You get 3 by 105, 1 by 35. And the other method is this other way of thinking about it. You can take the first ball and then without replacement take the second ball. And that would also give you the exact same probability distribution, and you'll get the exact same answer. Okay, so 3 by 15 into 2 by 14, and that will give you 1 by 35 as well. Okay, so I've put here a question for you. All right, so what would be the probability that x equals 0? And what is the probability that x equals 1? Okay, so let me give you, you've already calculated probability that x equals 2. I want you to think of how to do a very similar calculation, right? So you have to just go back and think about how x equals 0 can happen. You can use one of these two methods, okay? And then x is the number of red balls, okay? So you're drawing two balls random. So this is okay. So let me go back to the original questions. People want to see the original question. So here's the original question. There are 15 marbles with 6 green, 3 red, and 6 yellow. And x is a random variable that denotes the number of red marbles. And hopefully this is clear. Sorry. All right. So let me just go back to this question now. I showed you how to quickly calculate probability that x equals 2. You can use one of these two methods and quickly get to the answer. I want you to see if you can give me an answer with the probability that x equals 0 and probability that x equals 1. Okay, I'll give just a couple of minutes for people to put in this answer. Okay, so don't enter the answer in the Webex chat. You have to go to joinpd.com and enter the code that you see on the top right. And then you can see you'll get a box to put in your answer. You see people are trying to get to the answers, so only the responses are coming in. We'll give just 1 or 2 more minutes. I think this is good practice for you to understand how these random variables are defined in these kind of scenarios. Okay, so let me show the responses. You could have written it as fractions. I hope people have written this. No, people have not written it as fraction. Okay, 0.68, 0.34 seems to be a very popular answer. 628. So no one has written it as a fraction, I guess. These are just text. So there's a 6 by 35 that I'm seeing. There's a, okay. So it seems like 628. Okay, so there's some, so here. Okay, so 12 choose 2 by 15 choose 2 is the correct answer for x equal to 0. And so the way I would do it is I would find x equal to 0. For x equal to 0, I'd say it's 12 by 15 times 11 by 14, isn't it? Did you see how I got that? So probability that x equal to 0, you just take the method 2 and adopt it. Probability first is not read times probability second is not read given first is not read, right? What is the probability first is not read? It's 12 by 15 times first one is not read. Now you have 11 not read balls and 14 total. So it is 12 by 15 times 11 by 14, isn't it? If you do that, I think you'll get 22 by 35. That's probably 0.62 or something like that. Okay, that's x equal to 0. For x equal to 1, I would just do 1 minus. See, remember, x equal to 0, x equal to 1, and x equal to 2 are 3 disjoint events, and together they make up the whole sample space, right? So if you find probability of x equal to 0, probability of x equal to 2, all you have to do to find probability of x equal to 1 is just 1 minus probability of x equal to 0, probability of x equal to 1, right? So x equal to 2. So you get that in a very direct way. So that would be the okay. So so let me just, I know it took a bit longer for this question, but I know I was intentionally doing that because these are important. X equal to 1 and x equal to 2 are not disjoint. Why is that? Why do you say that? So if you have an outcome that corresponds to 1 red ball, you can never have 2 red balls, right? So those 2 are disjoint events. Okay, so yeah, so there's some intuitive explanations for, okay, so somebody wants method 2 for x equal to 1. Okay, so how would we do that? That's a bit more complicated, right? So you'll have to think of writing the probability of writing the event x equal to 1 in a more complete fashion. So it will be not read or read, not read and read, or read and not read, isn't it? So you have to use the, I don't know if you were in the first session or if you saw the video and the slides of the very first statistics session that we did. So I was explaining how to do these kind of problems, right? It should be not read and read or read and not read, isn't it? And then you do probability for that, and remember to, if you have to subtract, remember to subtract, okay? And then if you don't have to subtract, it's okay. You will get the correct answer. Okay, so you can do it. Okay. So, but the easier way to do probability of x equal to 1 is to find 0 and 2 and simply do 1 minus the sum of those two, and it's just also gives you the correct answer. I believe that will be 12 by 35. Okay, so these kind of problems are basic fundamental problems. So this will give you clarity on what an experiment is, what is the sample space, what are the outcomes when I put it together, what I mean when I do the probability calculation. So for x equal to 1, I believe the answer is 12 by 35. Okay, 12 by 35. So, so so these are important. Okay, so don't underestimate the basics at all, because quite often you'll be doing some calculation where the sample space may not be apparent, everything may not be apparent. From a high level, you'll be doing calculations with events, and and there'll be very ambiguous interpretations for many things. And if unless you sit down and be clear on the basics, you will never get the proper answer. Very confident about what answer to get there. So build up that confidence. Believe me, this basics is what will help you. Otherwise, in probability, usually you'll get an answer, and you will never be sure. There'll always be a probability that you're wrong, right? So that's not very nice. So it's good to be strong on the basics and be sure about the answer that you're getting, and work with the basics very carefully. All right, so we took a little longer for this, but that's okay. It's part of the process. So let's move on to the next question. Next question, I think, is relatively easier, but let's get started. Okay. So the next question gives you a discrete random variable x, does not talk about the sample space or experiment or anything like that. It's a very simple and straightforward PMF, right? So the PMF has been given, discrete random variable x, and there is a PMF for it, okay? And the question asks, what is the value of k? Okay, k is some unknown. What is k if this has to be a valid PMF for a discrete random variable x? So I'll give you a couple of minutes. This is a relatively easy, quick question. I'll give you 2 minutes, and then I'll share the answers that we put. Once again, don't answer on the Webex chat. Go to joinpd.com, put the code ijrzdc, and enter your answer there. You'll be able to see a box there, and you can enter the answer. So I'll give you 1 more minute. It's a relatively simple question. If you know the property of what makes a valid PMF, you'll be able to quickly answer this. Okay, so about more than half of the people have already answered. Let's wait for a bit more, and then we'll look at the responses. Okay, so don't put the answer on the Webex chat. Go to joinpd.com. It's there on the slide in Webex on the top right. There is a code on the top right that you have to enter. Okay, so I think this is a relatively easy question. Once you know it, it's easy to write down. You can see point 1 sort of dominates Oh, there's someone who's got the answer as 1. I don't know how they got that. So let's discuss that. 0.05. Somebody's got 0.05. Okay, 0.1 sort of dominates, and you can see some people have got 0.05. I don't know how they got that. Okay, so let's quickly see the solution. This is important. This is how you check if a PMF is valid. Each of the probabilities should be greater than or equal to 0. Okay, so none of this P of x equal to x can be negative. You can check. You need to check that. That's the first thing. And then if you add up all the probabilities of all the values that P of x equals x takes, you should get 1. Okay, so it's relatively straightforward to check if given PMF is valid or not. So you check these two conditions. So for the PMF to be valid, k plus 2k plus 3k plus 4k has to be equal to 1. So you should get 10k equals 1. Okay. So I am talking. I believe people can hear me. Can you not hear me?
Yes, sir. We can hear you.
Can you hear me though? Okay. So some people having difficulties. Okay. So you get k equals 0.1. Okay. So this is a straightforward problem, and so many of the problems you'll deal with may be as simple as this. Quite often, uh, it depends on what level you work at. You may not bother so much about the experiment sample space. You contrast the previous question with this question, right? You had to look at the experiment, look at the sample space, you have to understand the intricacies of how to calculate probabilities there, and finally you got a random variable. Okay, and here it's just the random variable itself is given, the distribution itself is given, the PMF itself is given, everything is just given to you, and you're asked to manipulate that, and that seems very very easy. Okay, and in many cases it may seem like this, but in many practical scenarios, it might be enough to know random variables and their distributions, and you work with them. It's not too bad, but often when you have to interpret something, see, right now this is just like a calculus addition problem, right? There's uh, uh, nothing to interpret about practical reality. Okay, so quite often probability is used to model something that's happening in practice in day-to-day life, and you do a complicated calculation and you have to interpret it back into how that impacts the reality. Okay, so to give you a concrete example, a lot of people use probability models for stock market. Okay, so you keep studying and seeing something in the model, and the model may do something and it may give you some answer, and using that you have to say, okay, I'm going to invest this much in this stock, that much in this stock. You take an action based on what the probability calculation is telling you, and unless you understand the connection between what is the experiment that you have set up and how these random variables come and how you can do the calculation and how you can go back, you will never be able to really truly understand how all those mechanisms work. Okay, so don't look down upon the first problem thinking only these problems are important. Both of them are very important. You have to understand how the random variable arose, what are the intricacies involved in that, do the calculation with random variables, and then go back to the practical or the experiment and make adjustments there depending on what you're trying to achieve. Okay? So think about that. This is just a high level thought on somebody was asking what is the practical connection and all that. So this is how people work with probability in practice. Okay? All right, so let's go to the next slide, which is another problem. This is again quite a straightforward problem once you give a PMF. Like I said, the rest of the problems in this exercise are quite simple. So once you have a PMF, usually it's very easy to work with it. It's very comfortable. It gives you simple answers. And here is one such question. There is a PMF given to you, and you have to find probability that x, or the random variable x here, whose PMF is given, takes value more than 3. Okay, so I'll give you just 1 or 2 minutes, and then we'll discuss. So there's a question on the slides. I think the slides are being distributed to everyone. There may be a 1 or 2 day delay in cleaning up the slides a little bit, if there are any bugs or something. In a day or so, you will get it. Okay. And the video also is on YouTube. There is I don't know. So I believe somebody from the course support team may be here, or maybe so you should the slides will eventually you should get it. So there's one answer from the ops team which says it is uploaded on the course. So you have to go check there. So the answering of questions once again in this session is on joinpd.com. So there's about more than half the people have looked at it. I've answered it. Let me just show the response now. Okay. 0.44 seems to be a very, very popular answer. Almost everybody gotten this 0.44, 0.44, 0.44. You can see why working with random variables in PMFs is so much easier, isn't it? Going back to the sample spaces where everybody gets confused, but those are the fundamentals. If you know the fundamentals, you can do way better than others. Okay, anyway, let's go back and see the question and look at how to answer that. So the first thing always to check in case if somebody gives you a PMF, you can just add it all up and check if it adds to 1, and yes, the PMF here is valid, so it's not a problem. So the main concept here is you have random variables and you can define events using the random variables. Okay, so note this down. Okay, so this is very important. Okay, so far we came from experiment and sample space to events and random variables, right? So quite often people will do the reverse. Okay, so they'll start with a random variable and start with a PMF, and they will define events using the random variable. Okay, once again I want to say it's reverse. It's not very difficult to do this. You can do this, but it's also important to understand the experimental setting. You go back to that later, but notice how we are doing it, right? So this is how you define events. Any equality or inequality involving random variables is an event. Okay, so that's sort of like a rough way of taking it. So for instance, here, what has been defined is this event x greater than 3. Okay, x greater than 3 or x takes value more than 3. You can imagine why this is an event, right? The experiment happened, an outcome happened. My random variable is a function of that outcome. Okay, is my random variable above 3? Okay, so clearly it's an event. Okay, so you go list all the outcomes which give you the random variable above 3. Okay, that is the event corresponding to x greater than 3. So you can see how random variables are defined. I mean, random variables end up being used to define events. Okay, and once you define these events, the old notion of computing probabilities for events will kick in. Okay, and all that comfort that you developed in calculating probabilities for events, you can now use. Okay, so events are conveniently defined using random variables, and you can do probabilities calculations conveniently using PMF for the random variable. So notice how this is done. X greater than 3 in this case is the same event as x equals 4 or x equals 5 or x equals 6. So notice I've used the word or there. You know what or means, right? It's sort of a technical word in probability. Okay? So x equals 4 or x equals 5 or x equals 6. Now you recall these three are going to be disjoint, right? An outcome that results in x equals 4, remember a random variable is a valid function, it's a proper function, but one outcome can give you only one value for the random variable x, it cannot give you two values. So if an outcome gave you 4, the same outcome will not give you 5 or 6. So these are disjoint events in your probability setup. Okay, so these are disjoint. So when you have disjoint events and OR, what can you do? What's probability? It is just probability of x equals 4 plus probability of x equals 5 plus probability of x equals 6. You just add the 3, you get 0.4. Okay, so now notice, Balaji, is my voice okay?
Yes, sir, it is fine, sir.
Okay. So see, notice you can do all the operations with these events, right? So you remember for events we had this the operations, right? You can think of not of this event, right? So x is greater than 3. You can do a not. Okay, what is not of x greater than 3? That's going to be x less than or equal to 3, isn't it? So now, from your familiarity with the event calculations, probability for event calculations, you know probability of not of an event is 1 minus probability of that event. Okay, so notice how you have to use all that, and conveniently, you can reduce your work even when random variables are involved if you know about events and how to combine them and how to deal with them. Okay, so this is very important as well. So probability that x is okay. Yeah, it's x less than or equal to 3 is 0.56. Okay, so 0.44 is probability that x is greater than 3. 1 minus that is 0.56. Okay, yeah, so 0.56. Some people are confused about the 0.44. Remember, 0.44 is probability that x is greater than 3, right? So that's the calculation we did just now. The probability that x is less than or equal to 3 is going to be 1 minus 0.44, the negation of that, right? So that would be 0.56. So I want you to think about this slide and what it means as you go forward in studying probability and statistics. So this is a very, very commonly used method. You start with a random variable and its PMF for distribution, and then you define events based on that random variable, and then start manipulating those events, calculate probabilities, and then it works like that. Okay, I hope you can understand that. Okay, so there's a comment or chat. Let me just quickly check that. Uh, okay. People are talking about my okay, 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 monotonic voice. Yeah, I guess it's difficult to avoid if you've been a professor for long. There's a student in my class who wears a T-shirt saying, "Professor is one who talks in somebody else's sleep." So one gets used to that. All right. Okay, so let's move on to the next question. These ideas are very important. Let me emphasize that once again. Okay, the idea that uh, the experiment and the sample space are used to define random variables, and from there, you can find the distribution, and anything you find from the random variable, you should be ultimately able to connect back to the experiment. That notion is very important, and equally important is this notion of starting with a random variable. So quite often, uh, the random variable is where you start with, and you keep defining events with the random variable. The sample space itself may not even be apparent. The experiment itself may not be even be apparent, but you'll keep working with the random variable and doing calculations. So both these things are very important in probability and statistics. You should have good comfort with both. Okay, so let's move on to the next question. This is like a small question leading up to the next question, which is maybe a little bit bigger. So I'll give you a couple of minutes to work this out and enter your answer. Go ahead. Oh, okay. I guess the setup made you enter a number. Okay, so I guess it shouldn't have been a number. Should have been, I don't know what people are entering. Okay, so it should have been text for you so that you could have entered. So it ended up being a number. I don't know. Maybe you can put the number without commas and spaces. Just put all the numbers together as one big number. You know? Just put the should be okay. Okay, so this is a relatively easy question, so I don't want to spend too much time on what people have done. It is just, yeah, 3579, most people have got that right. Okay, so let me just show you what, okay. Okay, so this is actually a bug here. Ignore that x equal to 1 line, that is wrong. It's 3579, it's not 3679. I apologize for that. So it's 3579. This, I don't know how this one came in, I must have just not noticed it. So it's 3579. It's just a direct plug and play, you know, just 2x plus 3. You put x equal to 0, 1, 2, 3. You'll get 3579. Okay. So I've asked a little question here. So I've asked you two things. What is probability that y equals 5? So y equals 5 corresponds to something. You can think of how to answer that. Then I've also asked you what is the probability that y equals 6? Okay. So I want to give a couple of seconds for you to think about this question because this will come up in the next question as well. So first of all, there's a typo on the slide. Ignore that. This is x equal to 1 is 3, 5. It's not, it's 5. It's not 6. It's a silly typo. So it's 3579. And then what I want you to answer is actually the question on the box here. Suppose somebody were to ask you, so we saw what's probability of x, right? So if I tell you what's probability of x equal to 0, x equal to 1, you know how to answer. Well, if I give you probability that y equals 5 or y equals 6, how will you go about answering that? Okay, so I can go to the previous slide. I think people want me to go to the previous slide. You can copy down the PMF if you like. It's 0.1, 0.15, 0.3, 0.45. So let me just quickly see the responses as they come up. Probability of y equals 5 is 0, y equals 6 is, people are still typing in. Yeah, so yeah, okay. So this answer that's here looks very nice. So you see probability of y equals 5 is the same as probability that x equals 1. Okay, so you put small letters y and x, but I guess you can use capital letter if you like. Y equals 5 happens when x is 1, right? So these two events will have the same probability. That's true. And y equals 6 has a probability of 0. There's no way y is 6. So that is 0. Okay. So keep that in mind. Okay. All right. So these are two questions as prelude. And that takes us to the next question, which is based on another idea called the cumulative distribution function. Okay, so this is once again an important notion in probability, and it's been discussed in your class. And we have a question based on that, and it combines the cumulative distribution function with this little device where we took a function of the random variable. So you have a random variable x, okay? Its distribution is given here. Okay, the cumulative distribution function for a discrete random variable x is given below. Okay, so that's this f of x function. The question asks you to find the probability mass function for y, which is 2x plus 1. Okay, so you need to know what the definition of the cumulative distribution function is. I would suggest that you sketch it. It's a simple sketch. Go ahead and sketch it. Then connect the random variables values to the cumulative distribution function. There's a way to connect it. And once you connect it, you can find the values and the probabilities. The PMF you can find from the CDF. So how you do that is the question. Once you do that, this answer is straightforward to do. Okay, so I'll give you a couple of minutes for it, and you can write out the response. No, there's no weighted average or anything. There is a way to convert it, okay, from the CDF. You can sort of identify the PMF. Okay, you identify the PMF, and once you identify the PMF, you can simply use what we did before to do the PMF for y equals 2x plus 1. So it's sort of like 2 or 3 steps in this problem. Should do it one after the other. Okay. And for those of you who felt that the probability was very tough, I think I heard a couple of comments saying probability is very tough. The initial parts of understanding the experiment and outcome, and how to do events and probabilities and what are the correct assumptions, and that part always trips people up sometimes. So one thing I can assure you is, once you come to the world of random variables, PMF and CDF and all that, things are often simpler. Okay, so you see, for instance, and once I gave you the PMF, it was just sort of straightforward, right? Many of the calculations involving the PMF are straightforward. So likewise, you'll see the initial very basics will be a little bit confusing in the beginning, and it's natural. It's confusing for everybody. Don't be alarmed or put off by it. Be patient, proceed to this notion of PMFs and CDFs and random variables. You'll see actually these are much simpler. Okay, it's always a simple method. And how do you find the PMF from CDF? It's a very simple method. How do you find the CDF from the PMF? That's also a very simple method. Okay, so both are very straightforward. How do you check whether a PMF is valid? How do you define events from random variables? How do you find probabilities for events from random variables? So these are all very straightforward calculations you can do with PMF, and you have to be patient, a little bit more patient with trying out the basics. I mean, you should, a lot of this basics will also be repeated in statistics too. Okay, so you'll have an opportunity to learn that again. It's very hard. I can tell you, seasoned experts make mistakes in probability basics. It's a bit misleading. A lot of it is about interpreting language and being lots of ambiguity in those definitions. So, uh, so, that's how it works. I mean, you'll be, a lot of experience is needed in getting over this. Okay? But like I said, the nice thing about it is most of the work will involve random variables, PMFs, CDFs, and other type of functions around random variables, and those are usually very mechanical. Okay? Uh, it's quite easy to do. Like I said, so far you can see the calculations involving PMF are so easy. They sound so much easier than working with the probability spaces. Okay, so I can see there are fewer responses. I think maybe people have not studied this in some detail, so maybe I should just jump to the solution and show you how this is done, or maybe I'll wait for a couple of more minutes. It involves a little bit of time, so I'll give you a few more minutes, maybe 2 more minutes. Then see, give you 2 more minutes, and then I'll show you the responses. Yeah, so you just enter the values taken by y and the probability. Okay, so if somebody asks you to describe the PMF of any random variable, you write down, okay, y takes value 0 with this probability, y takes value 1 with this probability, y takes value 2 with this probability. That's how you describe the PMF of a random variable. Okay, so I'll give you one more minute. I can see that not too many responses have come in. So maybe I should just go ahead with the solution. Okay, so let me show you the solution. So this is how you can find values taken by a random variable from CDF and also the probability with which it takes its value. Okay, so notice this. So this is a plot of the CDF, right? Can you see the plot of the CDF? You agree that this is a plot of the CDF? Okay, so you have the x-axis which goes 0, 0.51, etc. And for x less than 0, it is 0. For x between 0 and 1, it is 0.1. And between 1 and 2, it's 0.25. Between 2 and 3, it's 0.35. Between 3 and 4, it's 0.65. Then after 4, it is 1. Okay. So here are the two things you have to do. Like I said, I mean, it's sort of a mechanical process to go from the CDF to the PMF. Okay. You have to identify locations of jumps in the CDF. Wherever the CDF jumps, right, it'll either be flat or it'll be jumping. The locations of the jumps correspond to values taken by x. Okay, so where are the jumps happen at 0, 1, 2, 3, 4. So the jump locations are 0, 1, 2, 3, 4. These are the values taken by x. And the magnitude of the jump, how much it jumped by, is the probability with which x takes that particular value. Okay, so if you now go to 0, you look at so remember this is the CDF distribution function. How do you go from CDF to PMF? This is what you do. Okay, you from 0 at location 0, there's a jump. You can see that there's a jump, and the magnitude of that jump is 0.1. Right? Do you agree? The magnitude of the jump is 0.1. Right? So it went from 0 to 0.1. So the magnitude of the jump is 0.1. So the probability that x equals 0 is 0.1. Now, what is the probability that x equals 1? There is a jump of 0.1 to 0.25. The jump is from 0.1 to 0.25. So the magnitude of the jump is 0.15. So that's the probability that x equals 1. The same thing you repeat at every place it jumps. Jump at 2 is from 0.25 to 0.45. So that's 0.2. Okay. The jump at 3 is from 0.45 to 0.65. That's again 0.2. The jump at 4 is from 0.35 to 1. Oh, I'm sorry, 0.65 to 1. That is 0.35. Okay, so is there a dispute with any of these values? Somebody is saying, oh, what happened? Why do you say probability that x equals 1 is 0.24? Okay, so maybe I should show you the previous slide. It's 0.1. Oh, so the 0.1 you probably read it as 0.01. Okay, so that's why I think you wrote 0.24. The first jump is 0.1. Okay, 0.1. It's not 0.01. Okay, so 0.1. So you have 0.15. Okay, check it. It's just the magnitude of the jump. It should be okay. All right. So this is the mechanical way. Yeah, you can also verify that it needs to add up to 1. Okay. Right. So if you did the calculation right, if you add up all these probabilities, you should get 1. Okay. Otherwise, there'll be a error somewhere. Okay. Okay. All right. So this is the mechanical process that you have to use to go from CDF to PMF. Okay. You can sort of reverse it to go from PMF to CDF also. So you can see how you can go from PMF to CDF, right? If I gave you the PMF, how will you go to CDF? You have to keep cumulatively adding. Okay. So less than 0, it will be 0. From 0 to 1, it will be 0.1. From 1 to 2, it will be everything below 2, right? So you add up 1 and 2, 1 and 0, you get 0.25. So this process is an important and basic skill that you should have. It's like, addition, subtraction, and this probability. Okay, so you should be able to go from CDF to PMF and PMF to CDF. Okay, and you should know the jumps, and it's very easy to do in that fashion. Okay, so this is the first step. We are not done with the problem. The problem asks for one more thing. Okay, and that's not too bad. We have done this before. We know how this works. Okay, so x takes values 0, 1, 2, 3, 4. I'm interested in y equals 2x plus 1. That takes values, 1, 3, 5, 7, 9. And probability is quite easy to see. So probability that y equals 1 is going to be 0.1, 0.15, 0.2. Okay, so it's just sort of straightforward from that point onward. So let me just go now and see the responses and see if people sort of got this right. Yeah, I think many people have got it right. So yeah, 0.1, 0.15, 0.2, 0.35. Okay. So y, I mean, you don't have to say a range for y. I think people are looking at CDF for y. You can also PMF for y. That's okay. Okay, so most people have got the answers right. So maybe people who didn't do it, maybe they were not introduced to this method of going from CDF to PMF and working with that. That's okay. So that should help you. Okay, so those are the problems that I wanted to show you from the graded assignments, and there's about 20 minutes left. So I'm going to discuss one other problem. This is slightly different. It's maybe a practical sort of question. I don't know, but it's a question that is central to this entire program. Okay, these are the sort of questions that one will work with as we go to the next course, like statistics 2 or ML foundations or actual machine learning itself. One usually grapples with a question like this. Okay, it seems like you only learn probability. Many of you are probably not very comfortable worrying about whether this is something that's easy. There was a doubt about, oh, can you do this, etc. Let's just see if we can sort of answer a very simple question based on this PMF. So you have a random variable x, okay, and its PMF is known to you, okay. So in fact, even this is very hard. In reality, in most of the cases, you will not know the PMF. But let's say you know the PMF, okay. So I'm giving you a much simpler setting, okay. And given the PMF, you have to now okay, so what's the meaning of value of x? Okay, see, x is a random variable. Random variables typically take values. Okay, so remember, when you do an experiment, you get an outcome, and random variable is some number which is associated to the outcome. Like for instance, in the very first problem today that we did, you drew two balls, and you weren't content with the outcome being just two balls, but we defined a random variable which is number of red balls in the outcome. So then you got a number, right? So when you actually do the experiment, you will get one outcome, isn't it? And for that one outcome, you can compute the value of the random variable. Like for instance, you draw two balls, you got two green balls, then my random variable x, which is number of red balls, is 0. Okay. Likewise, there is some experiment going on here, some outcome is there. I haven't told you what it is. Maybe this is some biased die or something. I don't know. I mean, some experiment, I don't know what it is. But from that experiment, I have a random variable x. Okay, so notice, I mean, I don't need to know the details of the experiment. No, I mean, I know the PMF of x. And the PMF of x is given to me, and this is the PMF of some. I hope it's a valid PMF. Is it a valid PMF? I mean, if it's not, please adjust a little bit here, there. I think it's a valid PMF. Okay, somebody agrees with me. It's a valid PMF. Thank you. So, PMF like this is here, and then, so now you have to guess, right? You have to guess the value of x, and what the question asks, what will your guess be, right? So it's kind of a difficult question to answer, believe me. Okay, people have answered already. So I think if you know a lot of probability, I'm sure there's a subset of people here who know much more advanced probability and all that, and they will probably know all these things. But this is a sort of a very, how do I say it, a question which needs many more questions to be asked, right? Sometimes, there'll be a question and then 100 questions should come to you before answering it. And it's not enough to just ask this question. Worry about what it is. So, but let me just give a couple of more minutes and then let me see what the most popular answer was. It's just based on the PMF, if you have to guess the value of x that may happen, right? Let's see. Most people are saying 4, and 4 seems like a. Some people are saying 3.21. Wow, this is amazing. Okay, so these are people who I think are experts. Some people have put 1, 2, 3, 4, 5, 6. Let's say everything. Okay, so there's a 3.21. It's a mysterious answer, right? So I like, oh wow, there is a 6 point something into e power plus 34. I think somebody's just having fun at my expense, maybe. I don't know. So 4 seems like a popular answer. It's sort of well motivated. Why is 4 well motivated? I mean, you have to ask yourself, why 4? Why that strange 3.21? Okay. Let me give you a few thoughts on this. Okay. Here are a few thoughts. Okay. Whenever you want to guess something or find something, you have to ask what is the objective. Okay. There has to be an objective to doing this, right? And if there is an objective, you can try to maximize it or minimize it or something. Okay. So that's what I meant by saying for some questions, before answering, you have to ask more questions. Okay. So if I give you a PMF and I ask you to guess what value this random variable may take, you should turn around and ask me, what is your objective with this? So I guess, what are you going to do with it, right? So a lot of things on how you guess will depend on how I want to use that guess. Okay, and it's sort of difficult to imagine this, but one of the important criteria is to make a guess which will minimize the probability of being wrong. Okay, so you might want to do that. That's a good option. I put that as option 1, and that's the option that results in a equals 4, right? The guess equals 4. Do you agree? Out of all the guesses you can make, you're given only one guess, right? Out of all the guesses you can make, if you guess 4, you will minimize the probability that your guess is wrong, right? So notice, what is probability of x not equal to a? That's the probability that the guess is wrong, isn't it? And that's 1 minus probability of x equal to a, right? We know that from the theory of events and all that. So when you look at the PMF and pick the maximum, the value of x which gives you the maximum PMF, what you are implicitly doing is to minimize the probability of error, minimize the probability that you are wrong. Okay. So if that is what I'm interested in, if that is the objective I'm interested in, you have to guess 4. Okay. And there are a lot of people in the audience who have maybe seen these kind of problems before, but it turns out probability of error is not the only thing you may want to minimize. There may be other things that you may be doing, and for that, you may have to minimize other things. There is a very popular option to minimize something else, and I'm not even saying what that is. I'm leaving it as a mystery to you. And if you do that, then the answer will be 3.21. Where do these things come from? Just really, I think some people gave 3.21 as the answer, right? So you can see they do know ahead of time what is it that these things are. But even if you didn't, I want you to think about this and be a little mystified by it, right? Just for you to think about it. These kind of questions are very important to problem in areas like data science, machine learning, and all that. Okay, so here's a random variable. Here's the PMF. You have to guess what it is, and depending on what objective you have, what you want to minimize or maximize, your guess will be different. Okay, and that this is central to many things You may want to optimize other things as well. So 3.21 is not the only other answer. There are other answers. If you change the metric a little bit, what you want to minimize, you will get other things. So why A equals 4? I just gave you an answer. A equals 4 will minimize the probability that you're wrong. Okay. So notice 3.21. What a strange answer. I mean, the probability that you're wrong is 1. Right? If you say 3.21, you will definitely be wrong. Okay. So whatever answer you give, it be wrong. But you will see later on, if you continue to study statistics 2 particularly, you will learn why 3.21 is a good answer for this. Okay. And that's hopefully this is enough. This kindles your interest a little bit. A lot of people are saying this is a tough subject, etc. But this is very, very useful subject. Okay, so your ability to guess what will happen. Like for instance, when you want to go take insurance for your car, right, or you want to take life insurance, the insurance company is asking you for a premium. Right? So maybe many of you are students here. You don't know what is insurance. But some people are older people who may be buying insurance. So how do you think the insurance company comes up with a number for that? How do you think they set premium? Of course, there's competition. Of course, they can't be much higher than what other companies are charging. But how do they do this? Right? So they have to have an estimate of probability of whether you will get sick or not, right? Probability that whether your car will get into an accident or not. And all of that involves some probabilities and some guesswork of this nature. Okay, what do you think the insurance company is trying to minimize or maximize? Are they trying to maximize your well-being and health? You really think so? So the insurance company will have its own maximization metric, isn't it? Risk is something that you handle. You want to minimize risk, so you will choose certain insurance. But the company might want to be minimizing or not minimizing, minimizing its risk of loss, but minimizing their loss. And usually they're not really interested in minimizing their loss. They're interested in maximizing their profit, right? So how does that objective function translate into a condition on some random variables that they may have about how often, what is the likelihood of you getting into an accident, how big an accident it's going to be, if you're buying car insurance, for instance. So notice how interesting these problems are. How do you do it if you don't know the basics of PMF and CDF and all? Okay, so this is too early in this course for you to understand deeply what I'm saying, but at least you get a big picture, right? You get a big picture of where all this is leading. Okay? Somebody says insurance is a big scam. Okay? I'm not going there. I'm just trying to get you to think about some things where these kind of questions are very, very important. Okay? So it's a very simple question in some sense. And how you answer these questions depends on what your objective is, and depending on your objective, the answer will change, and you should know how these answers are arrived. Okay, so on that note, let's come to the conclusion of this session. We've done reasonable justice to the questions, I think. So somebody is asking, why do you want to guess? Why do you want to guess? Okay, so uh, why is a great question. So why? Because this is a quiz, this is a question, and I asked you. Okay, so not only that, but there's lots of practical value to such guesses. For instance, one might want to guess what the Sensex will be tomorrow. What will be the price of a stock tomorrow? Right? Why do you want to guess the price of a stock tomorrow? Because if you think it's going to rise, you will put money into it, right? It has direct meaning. So instead of thinking about these uh, probabilities as idle things, I just gave you a simple probability distribution, and this is exactly what happens day to day in the stock market trading companies, right? Why do you have to guess? Because you can make money if you guess right. Okay, it's one very simple way of putting it. That's hopefully that answered the question. Okay. Yeah, of course, you're still learning basics. Please continue to learn the basics. Be motivated by these kind of questions, but make sure your basics are very strong. And Okay, somebody is asking whether a data scientist will be rich. A good data scientist is highly likely to be rich. How is that for an answer? Okay. All right. Okay, so I think that should conclude the session. Thanks a lot to everyone for participating. Hope you had a good session, and happy solving the problems that are up ahead. Thank you. Bye-bye.
So tomorrow we have the session for computational thinking at 7:30 p.m. The link is given in your calendar. You can join using that, and it will be streamed on YouTube also for you to watch later. We are uploading the slides on the course, except that I just saw they have done it under that quiz and mock test thing. I've asked them to move it into the respective weeks that we will do it. So you can go back and watch the session, and we'll have the slides also for this. Somebody had asked about week 8 and 9 math slides pertaining to content videos. I know that we have not done that. We will do that. We have asked the faculty for that. We'll get it done. But Professor Andrew's slides of yesterday's and last week's and all are uploaded there along with the video. Okay? Yeah, Andrew, I'm done.
Okay, thanks for the clarifications. Thank you everyone. Bye-bye. We're going to close the session. Thank you.